In this video, we will look at the Maclaurin series, which can be used to approximate non-standard equations into polynomials. The formula for the Maclaurin series is also given in the formula booklet. Using this formula, what it means is that any expression of x or fx can be written as a polynomial as long as we know the values of the function and its derivatives at x equals to 0. So for example, given fx, we can find out f0, and also given fx, we can differentiate it to get f prime x, which allows us to find f prime 0. Differentiate it again, we get f double prime x, which allows us to find f double prime 0, and so on. And once we have all these values, we can substitute them into the terms inside the formula, and this will give us the Maclaurin series of the particular function. However, note that the Maclaurin series is used to approximate curves that are very near to x equals to 0, or rather very small values of x. The error will become larger as we move away from x equals to 0. To make use of the Maclaurin series formula to approximate any given function, we make use of the function y equals to sine x as an illustration. First, we will differentiate the given function for the required number of times. For example, if we want to approximate a function with a polynomial of up to and including the x cubed term, we will need to differentiate this function until we get the third derivative. So for y equals to sine x, we can differentiate it to get dy over dx equals to cosine x, d2y over dx squared equals to negative sine x, and finally d3y over dx cubed becomes negative cosine x. Next, we find out the corresponding values of these derivatives when x is equal to 0. So when x equals to 0, I know that y will be 0. dy over dx is cosine 0, which gives us a 1. d2y over dx squared is negative sine 0, which is 0. And finally, d3y over dx cubed is negative cosine 0, which gives us negative 1. And with these values, we can now substitute them into the formula and simplify. So eventually, we will end up with the term sine x equals to x minus x cubed over 3 factorial, and so on. And if we recall the standard series for sine x, we get the exact same expression. Thus, we know that the Maclaurin series is a general formula that can approximate any expression, including the standard series expansions. In example 1, we are going to do repeated differentiation to find out the Maclaurin expansion for tangent inverse x. So let's differentiate the few terms until we get a third derivative, since we need to expand until the x cubed term. So dy over dx will be equals to 1 over 1 plus x squared. d2y over dx squared will be equals to negative 2x divided by 1 plus x squared squared. And d3y over dx cubed, we have to make use of quotient rule to differentiate this, and it will give us 1 plus x squared squared times negative 2 minus negative 2x times 2 times 1 plus x squared to the power of 1 times 2x divided by 1 plus x squared to the power of 4. And I won't be simplifying this term over here because eventually I know that when I substitute x equals to 0, the 0 over here will make this whole term go away. So I'm not going to waste any time doing a simplification of this expression. Now I'm going to substitute x equals to 0. I will get y equals to 0. dy over dx equals to 1. d2y over dx squared equals to 0. And finally, d3y over dx cubed will be equals to negative 2 because this term over here gives me a 1 multiplied by negative 2, which is negative 2. This term becomes a 0 because of this 0 over here. And the denominator is a 1. So therefore, with this, I can say that tangent inverse x will be equals to x minus 2 x cubed over 3 factorial, and so on. and I can approximate this into x minus 1/3 x cubed. And this is the Maclaurin series for tangent inverse x. In example 2, what we want to showcase to you is that we do not need the function of y equals to fx at all in order for us to derive any Maclaurin series. We just need to have the values of fx, f prime x, and so on when x is 0. So for this example, we do not have the function for y as well, but it is okay. We are going to start from dy dx equals to x sine x plus ex. Now based on this, I can differentiate it dy over dx equals to x times cosine x plus 1 times sine x, which is sine x plus ex. And I should differentiate this again, the 3y over the x cubed gives us x times negative sine x plus 1 times cosine x, which is cosine x, and differentiation of sine x gives me another cosine x and an ex over here, which I can simplify into negative x sine x plus 2 cosine x plus e to the power of x. And thus, I can substitute x equal to 0 in to find out all the respective values. When x equals to 0, I'll get y equals to 1. This is given from the question. Next, dy over dx, if I substitute x equals to 0 inside here, I will end up with 1. The 2y over dx squared, this term will become 0, this term will become 0, and thus I'm left with e to the power of 0, which is a 1. And finally, for the 3y over the x cubed, this first term becomes a 0, 2 cosine x becomes 2 because cosine 0 is 1, and e to the power of 0 is 1, and therefore I get 3 for my third derivative. And with this, I can say that y can be approximated by 1 plus 1x plus 1x squared over 2 factorial plus 3x cubed over 3 factorial, and so on, which we can approximate into 1 plus x plus half x squared plus half x cubed. And this is the Maclaurin series of some given function where we do not know what the function definition is, but we know its first derivative.